What if the closest star to our sun hides a world where humans could one day live? 4 light-years away, Proxima Centauri b beckons, a planet in the habitable zone teasing the possibility of liquid water and life. But getting there? That's a 25 trillion-mile journey that defies everything we know. Buckle up. In the next 30 minutes, we'll unravel the mind-blowing science pushing humanity toward the stars, from interstellar propulsion to alien worlds and cosmic mysteries right in our solar system. Can we really reach another star? From Gagarin's first orbit to laser-driven sails, humanity's quest for the stars is closer than you think. Let's dive into the tech that could get us there. The dream of interstellar travel began when Yuri Gagarin orbited Earth in 1961, proving humans could survive space. This monumental achievement marked the dawn of human space exploration, igniting imaginations and aspirations for venturing beyond our solar system. Gagarin's journey was not just a leap for mankind but a giant leap for our understanding of what was possible. It set the stage for future missions and the relentless pursuit of knowledge about the cosmos. Apollo 11's moon landing in 1969 showed we could step on another world. Neil Armstrong's iconic words, "That's one small step for man, one giant leap for mankind," echoed the sentiment of an entire generation. This mission demonstrated our ability to not only reach but also explore and study extraterrestrial surfaces. The moon landing was a testament to human ingenuity, engineering prowess, and the unyielding spirit of exploration. It paved the way for future missions to Mars and beyond, fueling our desire to reach even further into the cosmos. The Voyager probes, now drifting in interstellar space, carry golden records, messages for alien civilizations. Launched in 1977, these probes have traveled farther than any human-made object, venturing into the unknown. The golden records they carry are time capsules, containing sounds and images that portray the diversity of life and culture on Earth. These records are a testament to our desire to communicate with potential extraterrestrial life and share our story with the universe. The Voyager missions have provided invaluable data about our solar system and continue to inspire us to look beyond our planetary neighborhood. But to reach Proxima Centauri, we need more than dreams. Proxima Centauri, the closest star to our solar system, is still a staggering 4.24 light-years away. This distance presents a monumental challenge, requiring advancements in propulsion technology, energy sources, and life support systems. Current spacecraft would take tens of thousands of years to reach it, highlighting the need for innovative solutions. The journey to Proxima Centauri is not just a technical challenge, but also a test of human endurance, creativity, and determination. Ion engines, like those on NASA's Dawn mission, use electrically charged particles for efficient thrust, but they're too slow for a 4.24 light-year trip. These engines are highly efficient and have been used successfully in missions within our solar system, such as the Dawn mission to the asteroid belt. However, their low thrust means they are not suitable for the vast distances involved in interstellar travel. To reach another star, we need propulsion systems that can achieve much higher speeds while maintaining efficiency and reliability over long durations. Enter nuclear pulse propulsion, a Cold War idea to detonate small nuclear bombs for thrust, potentially reaching 10% the speed of light. Too dangerous maybe. This concept, known as Project Orion, was developed in the 1950s and 1960s, and involved using a series of controlled nuclear explosions to propel a spacecraft. While theoretically capable of achieving high speeds, the risks associated with nuclear explosions and the potential for radioactive contamination have made this approach controversial. Despite its challenges, nuclear pulse propulsion remains one of the few concepts that could potentially enable interstellar travel within a human lifetime. But the Breakthrough Starshot initiative has a bolder plan. A light sail, pushed by millions of ground-based lasers, could hit 20% the speed of light, reaching Alpha Centauri in just 20 years. This ambitious project, funded by private investors and led by a team of scientists and engineers, aims to send tiny, lightweight spacecraft to our nearest stellar neighbor. The light sail concept involves using powerful laser beams to propel the spacecraft, allowing it to achieve unprecedented speeds. If successful, Breakthrough Starshot could revolutionize our approach to interstellar exploration and open up new possibilities for discovering habitable planets and extraterrestrial life. The catch? Synchronizing 100 million lasers is like threading a cosmic needle. The technical challenges involved in coordinating such a vast array of lasers are immense. Each laser must be precisely aligned and timed to ensure the light sail receives a continuous and uniform push. Any deviation could result in the spacecraft veering off course or failing to reach the desired speed. Despite these challenges, the potential rewards of successful interstellar travel make the effort worthwhile. As we continue to push the boundaries of what is possible, the dream of reaching the stars becomes ever more tangible. But why Proxima Centauri? Because it's home to a planet that could change everything. Could there be another Earth out there? Proxima Centauri b and thousands of exoplanets are rewriting our place in the cosmos. Let's explore these alien worlds. In 2016, astronomers discovered Proxima Centauri b, a rocky exoplanet in its star's habitable zone, where liquid water might exist. This discovery was groundbreaking because Proxima Centauri b orbits the closest star to our solar system, Proxima Centauri, which is just over 4 light-years away. The potential for liquid water makes it a prime candidate in the search for extraterrestrial life. Scientists have been particularly excited about this exoplanet because it lies within the habitable zone, often referred to as the Goldilocks zone, where conditions might be just right for life as we know it. Found using the radial velocity method, detecting a star's wobble from a planet's gravity, it's one of over 1,000 exoplanets identified since 1992. The radial velocity method has been a cornerstone in exoplanet discovery, allowing astronomers to infer the presence of planets by observing the gravitational effects they have on their host stars. This technique has been instrumental in expanding our understanding of the universe and the variety of planetary systems that exist. By measuring the tiny shifts in a star's spectrum, scientists can determine the mass and orbit of the exoplanet, providing crucial data about its potential habitability. The Kepler telescope's transit method, spotting dips in starlight as planets pass, revealed Kepler-22b, another habitable zone world 600 light-years away with a cozy 72 degrees Fahrenheit equilibrium temperature, assuming an Earth-like atmosphere. The transit method has revolutionized our ability to detect exoplanets by monitoring the slight dimming of a star as a planet crosses in front of it. Kepler-22b is particularly intriguing because its size and temperature suggest it could have liquid water on its surface, making it another candidate in the search for life beyond Earth. The Kepler mission has identified thousands of potential exoplanets, vastly increasing our knowledge of the cosmos. But what's the air like? Understanding the composition of an exoplanet's atmosphere is crucial for determining its habitability. The presence of certain gases, such as oxygen or methane, could indicate biological processes. Scientists use various methods to study these atmospheres, including observing the light that passes through them during a transit. By analyzing the spectrum of this light, researchers can identify the chemical signatures of different gases, providing insights into the planet's potential to support life. The JWST uses transmission spectroscopy to analyze starlight filtered through exoplanet atmospheres, hunting for water vapor, methane, or oxygen, clues to life. This advanced technique allows scientists to detect even trace amounts of these gases, offering a window into the atmospheric conditions of distant worlds. The James Webb Space Telescope, with its powerful instruments, is poised to make significant contributions to our understanding of exoplanet atmospheres. By studying the light that filters through these atmospheres, JWST can reveal the presence of molecules that are essential for life as we know it. Closer to home, LHS-12b, just 40 light-years away, may have an atmosphere, offering a Venus-like comparison to Earth. This exoplanet is intriguing because it provides an opportunity to study atmospheric conditions that are similar yet distinct from our own planet. By comparing LHS-12b to Venus, scientists can gain insights into the processes that shape planetary atmospheres and their potential for habitability. The relatively close proximity of LHS-12b makes it an accessible target for future observations and studies. These discoveries fuel our search for habitable worlds, but radiation, micrometeoroids, and decades-long journeys pose massive hurdles for human exploration. The harsh conditions of space travel, including exposure to cosmic radiation and the threat of micrometeoroid impacts, present significant challenges for missions to distant exoplanets. Additionally, the vast distances involved mean that any journey to these worlds would take many years, if not decades, to complete. Despite these obstacles, the quest to find habitable planets continues to drive scientific innovation and exploration, pushing the boundaries of what we know about the universe and our place within it. Before we chase distant stars, let's explore our own solar system, where Neptune's true colors and raging storms rewrite what we thought we knew. For decades, we pictured Neptune as a deep blue giant, thanks to Voyager 2's enhanced 1989 images. But recent studies by Oxford's Patrick Irwin using Hubble and the Very Large Telescope reveal Neptune's true color, a muted Uranus-like teal. Why the misconception? Early image processing exaggerated blue to highlight features. Neptune's atmosphere is a storm-charged spectacle, with winds hitting 1,300 miles per hour and the Great Dark Spot, a Jupiter-sized vortex. Mysterious hotspots at 750 degrees Kelvin defy its distance from the Sun, possibly from auroras or magnetic reconnection. Triton, Neptune's retrograde moon, spews nitrogen geysers and has a dynamic atmosphere that thickens in its 40-year summer. JWST's 2022 infrared images unveiled Neptune's dusty rings, unseen since Voyager, hinting at a complex interplay of methane clouds and atmospheric circulation. These discoveries refine our models for icy exoplanets far beyond. Now let's land closer to home, on the Moon's South Pole, where India's Chandrayaan-3 just uncovered secrets that could make lunar colonies a reality. In 2023, India's Chandrayaan-3 achieved a historic soft landing on the Moon's South Pole, a treacherous region of craters and perpetual shadow. This marked a significant milestone not just for India, but for global lunar exploration. The South Pole of the Moon is a region of immense scientific interest due to its unique environment. Unlike other parts of the Moon, the South Pole contains areas that are permanently shadowed, making it a challenging yet intriguing target for exploration. These shadowed regions are believed to hold water ice, which could be crucial for future lunar missions, and even for sustaining human presence on the Moon. Its Vikram lander and rover studied the lunar exosphere, a thin gas layer, and ionosphere, crucial for future communications. The exosphere is the outermost layer of the Moon's atmosphere, and understanding its composition and behavior is essential for future missions that aim to establish a long-term presence on the Moon. The ionosphere, on the other hand, is a layer of charged particles that can affect radio communications. By studying these layers, Chandrayaan-3 has provided valuable data that will help in designing better communication systems for future lunar missions. The CHASE instrument mapped subsurface temperatures, revealing lunar soil's insulating potential, 140 degrees Fahrenheit at the surface, but just 14 degrees 8 centimeters down, a boon for habitat design. This discovery is particularly important for the design of future lunar habitats. The extreme temperature variations on the Moon's surface pose a significant challenge for any long-term human presence. However, the insulating properties of the lunar soil could be used to create more stable and habitable environments for astronauts. By understanding how the temperature changes with depth, scientists can develop better strategies for building habitats that can protect astronauts from the harsh lunar environment. A seismic instrument detected a lunar quake, the first since Apollo, suggesting meteoroid impacts or tidal forces from Earth. This finding has significant implications for our understanding of the Moon's geological activity. Lunar quakes can provide valuable information about the internal structure of the Moon and the forces that shape its surface. By studying these quakes, scientists can gain insights into the Moon's history and its ongoing geological processes. The detection of a lunar quake by Chandrayaan-3 also highlights the importance of continuous monitoring of the Moon's seismic activity, which can help in assessing the risks for future lunar missions. The rover's laser spectroscopy found sulfur, aluminum, and iron, hinting at past volcanic activity but no direct water ice. Yet theories suggest it's trapped in shadowed craters. The presence of these elements indicates that the Moon has a more complex geological history than previously thought. Volcanic activity on the Moon could have played a significant role in shaping its surface and creating the conditions necessary for the presence of water ice. Although Chandrayaan-3 did not find direct evidence of water ice, The data it collected supports the theory that water ice could be present in the permanently shadowed regions of the Moon's south pole. This makes these areas prime targets for future exploration missions. Chandrayaan-3 paves the way for ISRO's Chandrayaan-4 sample return mission by 2028 and the Japan-India LUPEX rover in 2026, which will drill for water ice, a game-changer for lunar bases. The success of Chandrayaan-3 has set the stage for even more ambitious missions in the future. The Chandrayaan-4 mission aims to bring back samples from the Moon, which will provide scientists with a wealth of information about its composition and history. The Japan-India LUPEX rover, scheduled for 2026, will specifically target the shadowed regions of the Moon's south pole to search for water ice. Finding water ice on the Moon would be a game-changer, as it could be used to produce oxygen and hydrogen, essential for life support and fuel. This would make it possible to establish sustainable lunar bases, paving the way for human exploration of the Moon and beyond. Next, we journey to Mars, where brain-like terrain and ancient rivers hint at a wetter past and a future for humanity. Mars brain terrain, intricate patterns from ice sublimation and mud cracks found by Curiosity suggest a cycle of wet and dry periods billions of years ago. Ancient lake beds and river valleys confirm liquid water once flowed, while recent radar revealed equatorial ice deposits, reshaping our view of Mars' climate history. Sulfates in mud cracks hint at chemical reactions that could have supported microbial life, though no biosignatures have been found. The Perseverance rover's MOXIE experiment produced breathable oxygen from Mars's CO2-rich atmosphere, a breakthrough for sustainable colonies. Ingenuity, the first Mars helicopter, flew 72 missions, proving aerial exploration's potential. But challenges loom. Returning samples could cost $11 billion, and orbital debris threatens missions. Still, Mars's volcanic past, like Noctis Labyrinthus's canyons, and resources like water ice make it humanity's next frontier. But what powers the universe itself? Supernovae, like the one Betelgeuse might become, create the elements of life and hold clues to our cosmic fate. Supernovae are cosmic crucibles, forging elements like carbon and iron that form planets and life. Betelgeuse, a red supergiant 15 to 20 times the Sun's mass, has flickered dramatically, dimming in 2019 due to a dust cloud, not an imminent explosion. Its rapid rotation and pulsations, studied via Hubble and infrared telescopes, suggest it's in a carbon-burning phase, but a supernova is likely centuries away. The 2022 Boat gamma-ray burst, the brightest ever, disrupted Earth's ionosphere from 2.4 billion light-years away, showing supernovae's power. Type 1a supernovae, used as cosmic rulers, revealed the universe's accelerating expansion driven by dark energy. Future observatories like Vera Rubin will deepen our understanding, linking stellar deaths to the universe's structure. From Proxima Centauri B's tantalizing promise to Neptune's hidden hues, the Moon's south pole, Mars' ancient rivers, and Betelgeuse's cosmic drama, our universe is a tapestry of mysteries and possibilities. Breakthrough Starshot, JWist, Chandrayaan, and MOXIE are stepping stones to a future where humanity might walk on alien worlds or witness a supernova's birth. The cosmos isn't just out there, it's our next home. Keep looking up, because the stars are calling.